Hi everybody. So this is your instructions about the spreadsheet 4 assignment. What I'm going to be doing is working on this elephant data that I've been working on for the past couple of weeks. You can certainly follow along with me and do the same things that I'm doing on your copy of the elephant data if you want. What I want you to turn in though is your own data. So there's two options here. One is to go back to the data that you analyzed for the last spreadsheet assignment, look at the figure that you chose, a comparison, a relationship, a distribution, and choose the statistical test that you need to do in order to make that, in order to test the statistics on it. Or ideally, what you do is find a second data source that's related to your larger data analysis project. So what I'm encouraging you to do is to continue to build up the sources that you have to do this final project, which is due really in a few weeks. So I'm going to incentivize that a little bit in the grades, that you have another data source that you've done some kind of analysis on as your assignment for this week. But I want you to be able to do it. So if you're having trouble finding the data, or if you're not sure how to analyze it, you can certainly use what you did last week, because you should have a graph that has one of these things in it, a relationship or a distribution or a comparison. And you can just use that to show me that you've at least gotten the basics of how these statistical tests work. So remember why we're doing this. We're doing this because just having a figure that shows something visually isn't enough unless we have statistics behind it. So we need to know whether our statistical test gave us a result that convinces us that what we're seeing is different than what you might expect by just chance differences between samples, or what's a normal distribution of options in a population, for instance. So let's look at this slide, or this document. So remember last week I went through basically creating all of these different kinds of ways of illustrating these kinds of analyses. Comparisons using a bar graph, a relationship using a scatter plot with a trend line, composition, looking at the sex ratio of males and females in this time period, and then kind of more of a composition distribution with looking at the sex ratio before and after the Civil War in these elephants. So let's look at how we would, I actually also did this, we looked at this histogram, which is another way of measuring distribution. That I think is less common for you to do a statistical test on, and it's a little more complicated statistical test. So I'm not going to demonstrate how you would test this one. If you do have a data set where you want to do this, compare your distribution against some hypothetical or theoretical one, we can do that, but you will have to probably talk about how you do the analysis there. So let me show you how these different bits of analysis or different types of analysis can be done in Google Sheets, which is pretty slick, to be honest. So with this first one, we'll start here with the first one. I'm going to move these a little bit so there's room underneath for typing. So just making a little space here. With these, with a comparison, you're going to be using the underlying data to generate the p-value of the t-test. And in order to do that, first we have to make sure that the data that is underlying this, so the data we use to get the mean value for tusk length in these two time periods, is sorted on the original sheets. So we're going to go back to our working copies and just make sure that it's sorted. So no, this is not sorted by sex, which is what I need to do to compare all the males from one time period to another time period. So if you remember the way to add the ability to sort to a Google Sheet, you click on this row that has your headers in it, and then you hit the filter button, which looks like a little funnel. And then it gives you this upside down arrow, or yeah, this triangle, I guess, upside down triangle. And we're going to sort this data, and we're going to sort it, actually we'll sort it Z to A, because that'll put the males up on the top. So here are all the data for males and their test link, if it exists or not. And then we're going to do the same thing with the 2005 data. I'm going to go to the sex, and I'm going to sort it Z to A so that all the males are at the top of that data set. Okay, so that's the first thing I need to do, is make sure the data is organized so that I can use it in the figure, or in the analysis. Go back to our summary and figures page, and I want to calculate the p-value of the t-test for this comparison. And to do that, I just have to use a formula that's already built into Google Sheets. And the formula is the t-test. So I just start typing t-test, and I get this option down here, right? So I can just click on that, and oops, let me do that again. Somehow added an extra argument there. This doesn't always come up that you get like a good explanation of what's happening here, but I'm glad it did. If it doesn't come up, you'll have like a little question mark over here that you can click on, and you'll get at least this green part of the description. So this describes what you need for what the syntax is of the test, like what you're going to put in to get your answer. So here, this is telling me the kind of information I need to put in includes the range of cells that contains the data that is part of this average, basically, that I calculated. So for range 1, I need to go back to the data from the 60s, and I'm going to select, and see how the little the cell actually follows me over here. That's kind of handy, so you can see what you're doing. So I want to select all of the cells that correspond to the tusk length in males for that time period. So there's a bunch of blank cells here, but I'm going to include them. And I'm just selecting the cells that correspond, like I said, to the males in this population. So I started at the top, and I went all the way down to the last male on this list, now that I've sorted it. Then I put a comma in, so I type in a comma, and now I have to put my second range in, and that range is going to come from the 2005 data. And I go back there, again, I've already sorted it, so I'm going to collect this tusk length data, select it all, until I get to the end of that male list. I know it's a little bit hard to see with this over it, but I can tell that I'm on the last M there, and I'm going to put a comma in. Now the next things I put in, you're just going to have to trust me on this. There are different values for how many tails are in this test, and we're always just going to use 2. There could be 1 or 2. We're always just going to use 2. Did that go in there? 2. And then another comma, and I want to know what, that was period, another comma. And now I want to know what type of test I'm going to do, and there's 3 types here. We're just going to always pick the second type. So it's always 2 and then 2, and then close parentheses, and that's going to generate the p-value of the t-test. So here's my p-value of the t-test, which is asking me whether this difference in tusk length in males is real. So that there was a decline in tusk length in males between the 60s and the early 2000s. Is that significant? Is it repeatable? Is it something that is consistent based on the population? And we do that by looking at, or based on the data that we've collected, we determine that by looking at the p-value. So remember, the p-value, if a p-value is below 0.05, then it's a significant result. In other words, it's different from the null hypothesis, the alternative, which is that there is no difference between these two populations. So this tells me that this was a real decline in size. I might, if you're going to use this in like a figure title, which we'll get to at some point, you don't want all of these decimal places. I don't think it's just too much. So I'm going to reduce that by a few. But it still keeps us below 0.05. So that's how you do a t-test. Very straightforward, generates a p-value, pretty easy to do. Let's move to this one. This is also going to generate a p-value, but it's a slightly more complicated. So if we want to look at the sex ratio of males and females in this time period and compare it to a theoretical possibility, what we want to do is know what we expected. So we have the actual numbers, which are right here, and then we want to think about, well, what are the expected numbers? So the expected numbers would be, most or animal populations, because of the way they reproduce, should produce the same number of male and female offspring. So you would expect the ratio of males to females to be 1-to-1, or the percentage to be 50-50, right? So to figure out what 50-50 would look like, I need to know what the whole population is. So I'm going to calculate the total here, and Google already made that choice for me about what I wanted. But if I didn't know, I would type in sum, and it's summing up this little those two numbers there. Oh. And that gives me, oops, it also included it in my figure. I don't like that. Let me just get out of here. I'm going to put my total somewhere else so it doesn't mess up my figure. Total, and we'll call that the sum of these two numbers. And then my expected females would be half of that, right? So equals that divided by 2. And my expected males would also be half of that. So that divided by 2. So if the population was 50-50, this is the rate, this is the number of females and males, was exactly 50-50. This is the number of males and females that we would expect. So what we're asking is this distribution different from 50-50? And that's what the chi-square test will tell us. So here we want to put in the p-value of the chi-square test. And this is a very simple test. We're just going to do, type in chi. You get a whole bunch of different options that start with that chi. What we want is the chi test. That's the Pearson's chi-squared test. And here we just want to include the observed range, which is the actual numbers, and the expected range. So the observed range is here. We put in our comma, and now we put in the expected range, which is here. And we put our end parentheses in. And we get a p-value of 0.25. Again, I'm going to make that a little bit smaller just to make it less hard to read. And you can see that that number is above 0.05. So even though this isn't exactly 50-50, we can't say that the males and female population was significantly different from 50-50. This falls into what you would expect out of normal variation in a population in terms of males and females. So that's a chi-square test. We can do the same thing with this before and after the Civil War. We might ask whether the males and females after the Civil War were different from 50-50. So from that, we could do the same thing here. We're going to do total or sum there, and then expected. What is it doing here? No, okay. I wondered what it was suggesting as the autofill. So we're just going to do what I did before. Oh, okay. So the autofill is giving me the same equation as it did. So half of 161 is 80.5. I know that's not realistic. Like there aren't half females and half males walking around, but you still just use the numbers that are generated. So that to do that comparison, we're going to do so male female ratio in 2005 period. This would be the p-value of chi square, and we're just going to do equals chi test, and again we're going to pick our ranges. So there's what we observed and what we expected, and that gives us a p-value pretty close to 0.05, but it's still a little bit below it. So you can see that the this supports the hypothesis that, which we didn't even really state, that males were selectively lost from the population during the Civil War. So there's a higher proportion of females than males. Another kind of comparison test that you might do is comparing one group to another group rather than something against a theoretical. And in that case, you want to make these numbers so that they have the same relationship to each other as in the expected level, or in the reference level. So we want to see if the ratio is the same in 2005 to 13 as it was in 66 to 68. We would multiply these numbers from 2005 and to 13 by the frequency that they were in the population. So we could say expected if same as 60s. So that would be, for the females, it would be 93 times this percentage, 52.8, which as a proportion is going to be 0.528. And this would be this number times 0.472. Okay, and I don't want to go, this is asking me if I want to go back to the same value that I used up here, which I don't. So there. Okay. So now what's the this is male female in 05 compared to 66. Again, we have a p-value for the chi-square test, and this time we're just using a different distribution. Chi test, observed, expected. Ooh. Let me go up a few decimals here. I wonder why it gave me a 0. I might have done something wrong there. Let's try it again. Chi test. Observed, comma, okay, chi. Well, I wasn't expecting that number, but I think it just means that it's very tiny. Let me see if I can look at it in scientific. Ooh. All right, not sure why that's 0, but something to work on here. Sorry about that. But hopefully at least you get the point that we use the chi-square to get these relationships. Oh, I think I know what I did. So these numbers are way different. I needed to figure out what the total was and then use that as my source. So it's going to be not 52.8% of the number of females, but 52.8% of the total of the population. So that's where I messed up. So this is going to be this total number, which I already knew was down here. Yep, and I messed up our graph too. So let's change this. Instead of I-12, I want to use not that. Oh boy. All right. Okay, so I'm just going to get rid of these equations, or get rid of these numbers here, and we're going to go again, and we're going to figure out the expected females is going to be this number times 0.528, and the expected males is going to be this number times 0.472. That's the real expected numbers in the whole population. So then when I do the chi-square, I do get a number that makes more sense. Let me make this not scientific. Okay, so this tells me actually that ratio is not, that's not really different this way. That's interesting. Very interesting. Make sure that I've got the right numbers here. All right, well, not significantly different. Okay, this is how data analysis goes. You're kind of figuring it out as you go along. So the ratio, the male-female ratio, it's interesting, is not 50-50. Clearly not 50-50 in 05 to 13, but it's not significantly different. The ratio itself is not significantly different from 66 and 68. So that slight bias for females in 66 to 68, even though it was not significant, is enough to make this comparison close enough. All right, the last comparison, or the last statistical test we're going to do here is this test for relationship. And this is using a different, doesn't generate a p-value initially, it generates an R value. So the R value runs from somewhere between -1 to 1, and the closer it is to either end of those, -1 or 1, gives you the whether it's a close fit or not. So we're going to use, this is Pearson's R. We're going to use the equation or the formula Pearson. So if you start to write that in, P-A-R, what the data that you put in here is the ranges of data that you used to generate this figure. So those are over here. So that's age and tusk length. So I want age, all of those numbers. That's my first range. And then I want tusk length. And that's my second range. And that generates an R value of 0.8. So remember, this is different than the p-value. 0.8 is actually a pretty tight relationship. 0.6 would be the lowest we would say is a close relationship. Now, like I said before, there is a way to calculate a p-value of this, but I'm not going to do it now because it's 4 more steps, and something that we will address probably on a case-by-case basis if you do this kind of analysis and you want to see a p-value. But the tight correlation might be enough for our data analysis. So this will be something that we deal with as you're working through on an individual basis. Okay, so sorry for a little bit of fumbling around on the chi-square test. I think I'd like to show you when I'm kind of working things through. I promise it's not just laziness, but I think it's worthwhile to see me making mistakes too and kind of working through those. But now at least you have a sense about how you can generate a comparison or a statistical test that looks at your actual analysis that you're doing and tells you how much you can interpret from that analysis. All right, good luck with it. As always, send me questions if you have them. Thanks.